Hello, this is the third part of the chapter 6.3, and we will talk about properties of orthogonal projections. And just to remind you that we are looking at the projection of the vector y into the subspace W, and the projection formed by this vector, which we call y hat. And we talked before how to find this projection, but most interesting properties of this projection that it's actually provide us the closest point to our vector y. And our best approximation theorem tells you that if we measure the distance between our vector y and the projection y hat, this distance always will be shorter than any other point in the subspace W. So if we take point here, 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 anywhere else in the subspace W, the distance between our vector and that point will be larger than our projection. And that's why our projection y hat, sometimes called the best approximation of y, or you sometimes see it referring as the optimal projection or optimal distance. So it's always the closest us to our vector. Let's just try to practice finding the shortest distance. And it's mostly like, the problem here is mostly about the wording. Again, we are given the orthogonal bases U1 and U2, and the subspace W stand by the orthogonal basis, orthonormal basis U1, U2. And we are looking for the shortest distance between our vector y, given here, and the subspace W. And because we have an approximation theorem here, we know that what we're actually looking for is the distance between our vector y and its projection. So, and again, we will use the result, so form in the theorem 5, so the orthogonal basis theorem, we'll keep using it. So you probably should be comfortable now of how to expand vector y along the given orthonormal basis. So all we have to do is find appropriate weights C1 and C2. And for C1, we just need to find the dot product of our vector y in basis vector U1 and divide it by the dot product of U1 into itself. And the numerator give us 15, numerator give us 15, denominator is equal 30. Then we will repeat this process for the second weights, C2, and the numerator give us minus 21, denominator give us 6. Please repeat this calculation independently when you are done watching this video. Okay, so now finally when we find the weight, we can expand our vector y along the basis U1, U2 and find our projection y hat. So we take the weight C1 multiplied by the basic vector U1, take weight C2 multiplied by the basis vector U2. So, and that will give us a new vector projection, which basically give us 3 coordinates for the point which closest to our vector y, but belonging to the subspace W. Okay, so let's find the difference between our vector and its projection. And we call it, of course, z, but we don't have to use this. It's just easier to use the notation. Okay, so we take our original vector y and subtract the projection y hat, which we found in the previous step, and it's give us the vector z. So now our question here was actually to find the shortest distance between the vector and the subspace, which is a length of our vector z, or length of vector y minus y hat. So let's use the distance formula to calculate. So our distance squared should be equal all component of our vector z raised to the second power. So the first component 0 raised to the second power gives us still 0, the second 3 square, and the third one 6 square. So the total will be a 45. So, and this is the square of the distance. So to find the distance itself between the vector y and subspace w, we need to take the square root of the previous step, or square root of 45, or 3 square root of 5. So, and this 3 square root of 5 will give us the shortest distance between our vector y and the subspace w. Okay, so now this is the time for you to go at the end of the chapter and practice several exercises applying best approximation theorem. And again, for the next few chapters, we will use the best approximation theorem extensively. And actually, most of machine learning algorithms use this approximation.